Hi everyone, my name's Dimity, and in this video I'm going to talk to you about our approach to the third Probabilistic Object Detection challenge, where we used an ensemble of experts. An object detector localizes and classifies objects within an image, with a bounding box for the location of the object and a class label and confidence score to identify the object type. This makes object detectors really useful as sensors aboard robots or autonomous systems, and they inevitably use this perception to perform an action on the world. While this can make object detectors really useful, there can be problems when in the real world they actually perform more like this. As you can see in this image, the dog hasn't been correctly localized, with its paws and its tail being partly cut off by the bounding box, and the cat has been mislabeled as a dog with a really high confidence score associated. Probabilistic object detection extends upon standard object detection by now also requiring an uncertainty with the localization and classification of each object. As you can see on the image on the right, each bounding box now also has a spatial uncertainty that's expressed as a covariance matrix on each corner. And rather than just having a single class label with one confidence score, we now have a distribution of confidences over class labels. Ideally, these uncertainties should reflect any inaccuracy in the localization and classification of each object. One way to obtain uncertainty and perform probabilistic object detection is with ensembles. With this technique, we have a number of different detectors, which have all been trained separately and might even have different architectures. When we test these detectors on the same image, we will then get slightly different results in the localization and classification of objects. By gathering each detection and associating them based on the object they're detecting, we then have some variability expressed about the localization and classification of the object. We can then merge these detections into final detections and find a way to obtain the spatial uncertainty and label uncertainty. This is the approach we used for our submission to the Probabilistic Object Detection challenge, where we assembled an ensemble of experts. Our ensemble consisted of a number of high-performing object detectors trained on COCO, including Efficient Det D7, Detector RS, and Cascade RCNN. As you can see, each object detector had its own individual strengths, and we hope to leverage these to create an even better performing ensemble of experts. Efficient Det D7 had the greatest recall or detection rate and wasn't overconfident on false positive detections. Detector RS, on the other hand, had the best label precision when detecting objects, and Cascade RCNN had the best localization of objects. In order to group the detections from each individual detector, we used a ranked ensemble clustering process. I'll now go into an example of how this works, and you can see the exact algorithm in our workshop paper. To begin, we ranked the detectors from best to worst performing on the validation dataset of the challenge. In this case, Efficient Det D7 was the best performing, followed by Detector RS, and then Cascade RCNN. We first started with the best performing detector and took all of its detections onto our final image. We then attempted to see if any of the detections remaining in Detector RS and Cascade RCNN could be clustered with these detections. To determine if detections could be clustered, we examined the intersection over union between their bounding boxes, where they needed to have an IOU of greater than 0.7 to join the cluster. In this case, the bed and chair detections from both Detector RS and Cascade RCNN could be clustered. Notice that we still keep the red bounding box, which is detecting an orange in the background of the image that was detected by Efficient Det D7, even though no other detectors detected that object. We then move to our next best performing detector, in this case Detector RS, and take any of its unclustered detections that are remaining into our final image. We then examine the lower performing detector Cascade RCNN and see if any of its remaining detections can be clustered with this detection. In this case, Cascade RCNN hasn't detected the bottle, and so doesn't have any detections that can be clustered. We then move to the last remaining detector, Cascade RCNN. While Cascade RCNN has one detection of the photo frame that hasn't been clustered, it is our worst performing detector, and so we simply discard any detections that haven't been associated. After finishing the ranked clustering process, we then form our final detections by taking the mean of the label distributions and bounding boxes within each cluster. We also create a spatial uncertainty with a diagonal covariance matrix of the variance of each bounding box coordinate. For clusters that only have one detection, such as the bottle and the orange, we simply used a fixed diagonal covariance matrix of 15 pixels. Our submission also uses an adaptive gamma correction technique on the data. Images in the dataset have various levels of lighting, including dimly lit scenes where object detection performance suffered. Gamma correction is a non-linear operation that is applied to the luminance levels of an image, giving the effect of brightening images. For each image in the dataset, we find the gamma level to correct the mean image luminance to a desired value of 125, and apply gamma correction with this value. A number of examples are shown on the slide. The top layer shows the images in their original form, and the bottom layer shows the corrected images and the gamma level that was used. We used a minimum gamma level of 0.4, as lower levels than this gave noisy and grainy images. In this slide, we show the performance of each detector alone, as well as our final expert ensemble on the validation dataset from the challenge. As can be seen, our expert ensemble gets the best PDQ and a greater number of true positive detections than any individual detector alone. As mentioned earlier, each individual detector has its own performance strengths. By ensembling the detectors, our final expert ensemble achieves a middle ground in performance in each category. In our workshop paper, we explore this in more detail by looking at the performance of each detector on different object sizes and object classes, as well as the calibration of each detector's confidence scores. On the test dataset for the Probabilistic Object Detection Challenge, our expert ensemble tested on gamma-corrected data achieves a final PDQ of 22.85. Thank you for listening to this talk about our submission to the Probabilistic Object Detection Challenge, and please don't hesitate to send me an email if you ever want to discuss uncertainty in object detection.